Boa tarde a todos. Dando continuidade ao conteúdo de progressos e métodos, vou ler esse capítulo 4 desse trechinho de livro aqui. Patch Clamp Techniques for Single Channel and Roll Cell Recording. Introduction. The patch clamp technique was first used by Neuer and Sackman 1976 to resolve currents to roll single acetylcholine activity channels in cell-attached pathways of membrane from skeletal muscle. The method they used described by Neer, Sackman, Steybusch, 1978, and the subsequent refinements, Raymond Martin Neuer, have led to techniques for high-resolution recording of current in exquisite membrane patches. In addition to those that remain cell-attached, single-channel recording yields information about unitary conductance and kinetic behavior of ionic channels, already partly investigated by classical voltage clamp and by noise analysis. It is also leading to the discovery of new classes of ion channel, together with the method of roll cell recording, which permits the application of a voltage clamp to cells that are too small for microelectrode methods. Patch clamp techniques also permit investigations of the physiological role of ionic channels in cells otherwise inaccessible to voltage clamp and to cells that are not electrically excitable. 2. Method for patch clamp recording. The principle of the method is to isolate a pathway of membrane electrically from the external solution and to record current flowing into the patch. This is achieved by pressing a fine polished glass pipette, which has been filled with a suitable electrolyte solution against the surface of a cell, and the applying light suction provided by the glass pipette and cell membrane are clean. A seal rolls electrical resistance is more than 10 gigawatts gigaohms is formed. Under such conditions, that glass pipette and the cell membrane will be less than 1 nanometer apart. A high seal resistance is needed for two reasons. First, the higher the seal resistance, the more complete is the electrical isolation of the membrane patch. Secondly, a high seal resistance reduces the current noise of the recording, permitting good time resolution of single-channel currents. Currents whose amplitude is in the order of 1 picoampere. Figure 1 illustrates an equivalent circuit for the recording setup. The fraction of the current flowing through the path that will be collected by the recording pipette is RCO divided por RCO mais R pipette, where RCO is the seal and the R pipette the pipette resistance. As figure 1 also illustrates, it is necessary that the path from which recordings are made be small in area, compared with the area of membrane of the cell as a whole. In terms of figure 1, it is necessary that a cell menor que R path. If single-channel currents are not too after the membrane potential of the single significant significantly. Current voltage, amplifier pipette, CO, cell, external solution, by electrode, HERF, external amplifier. Figure the relation of a pipette to cell and the equivalent electrical circuit during path clamp recording. The opening of an ion channel is representation as the closing of the switch in figure U1b. The pipette resistance and the seal resistance are in series between the amplifier and the HERF, the external solution, and the path and the cell resistance are in parallel with the seal resistance in this path clamp tanks. The background noise level is also minimized by a high seal resistance. The variance of the current noise in área quadrada through a resistor is related to Johnson voltage noise due to the resistance being given by S1 4 kT FC per resistance. There K is Boltzmann's constant, T is temperature Kelvin, and the Fc is the bandwidth Hz in the low pass filter setting. Thus, for a 10 gigaohms resistor at 20 graus, the standard deviation of the current noise at 1 kilowatt kHz will be 0.04 picoamperes, but for a resistor of 100 megaohms it will be 0.4 picoamperes. In the recording situation used in patch clamp figure E1, resistor current noise will depend on how the resistance pathways to ground from the amplifier input decreasing as resistance increases. Since the path resistance is high, approximately 100 gigaohms or more, the low CO resistance predominates and will result in noise that will prevent good resolution of currents is smaller than 4 or 5 picoamperes. Such was the situation in the earliest path clamp experiments, where the CO resistance was less than 100 megaohms. In spite of this difficulty, information was obtained about acetylcholine activation channels, about the blocking effects of local anesthetics on such channels, and about glutamate activity channels of insect muscle. The achievement of gigacells, hierarchy 1 gigaohms, however, radically improved the quality of recording and made it possible to study channels of lower unitary conductance. Such COs are generally achieved in a all-or-nothing fashion and result in a dramatic improvement in signal-to-noise ratio. The conditions that appear to be required for the formation of a gigacell are the following. First, the surface membrane of the cell used must be clean and free of extracellular matrix and connective tissue. Cells in tissue culture are often preferred. Adult cells generally must be cleaned enzymatically or mechanically. Second, solutions should be free of dust and of macromolecules such as the components of serum in tissue, culture, media. Solutions are filtered using 0.2 micrometers filters of the detergent-free type. Cells cultures are washed several times to remove serum. Thirdly, the pipette tip is cleaned often by fire polishing. Fourthly, during the period just prior to cell formation, a small positive pressure is applied to the pipette to generate an outflow of solution through the pipette tip and so keep it free of debris. Loose pad clamp. In certain situations, however, a low seal resistance can be advantage, such as a method is the so-called loose pad clamp, developed to allow measurement of the distribution of ionic channels over cell membranes and making use of the low resistance seal and the resulting gap that will exist between membrane and the recording pipette to permit investigation of the lateral mobility of ionic channels. Here large diameter, approximately 10 micrometers. Pipettes are used to collect current from many ionic channels at the same time. Currents that are collected by the pipette must be multiplied by a seal factor to correct for the fraction of the membrane current that flows to ground to roll the resistance of the seal. The method has been used to investigate sodium channels of skeletal muscle channels that are activated by stepping membrane potential. Changing the voltage of the inside of the pipette to achieve this change in membrane potential will result in large currents flowing through the resistance of the seal to the grounded bed solution. This leakage current must be subtracted. Additionally, the voltage applied was the reference must be bigger than the desired change in membrane potential by the seal factor to correct for the division that occurs between pipette and seal resistance. These corrections can be applied by a mixture of analog and digital means. If a single pipette is used to correction can be made for an additional source of error, activation at an uncontrolled voltage of the ionic channels in the membrane under the ring of the pipette where the seal is formed. Concentric double-barreled pipettes have been used to remove this source of error. Gigaseal pad clamp. Cell attached and excised pathways roll cell recording. Figure 2 summarizes the main modes of gigacell recording. Much work is done using patches in the cell attached mode, but the resting potential of the cell is not known and neither intra nor extracellular ionic concentrations can be changed easily. For these reasons, it is sometimes essential to work using a cell-free mode with excised or ripped off fats. There are two kinds: inside out, made by pulling the membrane patch of the cell into the bed solution; outside walled, made by applying suction to destroy the membrane isolated by the patch pipette and then pulling the pipette away from the cell. The membrane should heal to give the patch of membrane whose intracellular phase is in the contact with the pipette solution. Roll cell recording is achieved by destroying the membrane fat using suction to the cell wall's interior then comes into contact with the solution in the pipette, maybe voltage or current clamp. The cell contains equilibrate over time with the solution within the pipette. Further details of these models are given below. Giant paths and measurement of pump currents. A procedure was been described for making gigacells with large diameter pipettes, 10 and 25 micrometers, and it was been used to study electrogenic pump and exchange its transport to where the unitary currents are small. It uses one of a variety of lipophilic glues, paraffin mineral oil, alpha tocopherol, to improve seal resistance and produces large areas of electrically isolated membrane. Current generation by ion exchange process such as the sodium and calcium exchanger, the sodium pump, and many exchangers driven by the electrochemical gradient on Na are too small to resolve as unitary current, and in normal size pathways are not present in sufficient number to generate a measurable current. In large pathways, currents due to exchangers and pumps are well resolved. They are used specifically in the inside-out configuration to permit changes at the cytosolic surface that modify the rate and characteristics of transport measurement as the pipette current. PET clamp techniques contains extracellular solutions, cell attached and inside-out pathways, cell attached pull inside-out pathways, roll cell recording, and the outside-out paths form a gigacell. Apply strong suction to achieve roll cell recording model. Pull outside out pathway. Diagram illustration the methods of making cell attached and inside out pathways and panel, and the roll cell and outside out pathways. 3. Instrumentation of a single channel recording. A diagram of the essential features of the amplifier used in the head stage of PET clamp is shown in figure 3. Essentially, this amplifier is a current to voltage converter with a high gain, owing to the large feedback resistor R, and which is arranged so that the potential inside the pipette V reference may either be held at a steady level or changed in a stepwise fashion. A description of the path amplifier is given in Capture 14.16. But the following points may be considered here. The input of the amplifier was GFET transistor of low leakage current and noise. Pipette outside the reference schematic diagram of a head stage current voltage amplifier. The gain it's by his feedback resistors, very subtract from the outside at the large stage. Level current and noise level that experimenter needs to take care to avoid damage to these from static potentials, for instance by simultaneously touching an earth when connecting a pipette. 2. The feedback resistor determines the sensitivity, the background noise level, and the range of the current measurement. If E is the path membrane current and V out V reference voltage, the voltage output. The feedback resistors contributes current noise with decreases inversely with the resistance, was described above. The variance of current noise at bandwidth Fc is given by Sc. It follows that for low noise, high gain recording should be high, say 50 gigaohms. However, since V out will swing by a maximum of only 12 volts, the output of the head stage will be saturated if E exceeds 240. Acho que é isso. Picoamperes. In roller cell recording, currents may often exceed this level. The value of R must therefore be chosen to suit the experiment, whether by prior selection of a suitable head stage or by using an amplifier that enables the experimenter to shift the value of remotely. Several commercial instruments possess later facility. Alternatively, a good compromise may be achieved with a fixed 5 or 10 gigaohms resistor for reference. Capacitor feedback. The noise associated with the feedback resistor is eliminated by using instead a capacitor to feedback current to the inverting input, producing an output that is the integral over time of the pipette current. To correct for this, the output is taken via a differentiator stage. The improvement in signal to noise is about 30% when noise from other sources is minimized. A worthwhile improvement for high-resolution single-channel recording. The disadvantage is the need to discharge the voltage on the capacitor as the output voltage limit of the amplifier is approached, producing a reset transient with a through brief 50 microseconds may occur frequently with large stating currents such as those encountered in roller cell recording. 3. The potential in the pipette is equal to voltage reference. This potential is set for zero current by offsetting electrode potentials at the beginning of the experiment. This can be done either manually or by using the search mode or tracking mode of the path clamp amplifier. which uses an integrator to keep its current at zero, adjusting voltage reference accordingly. accordingly. Once a high resistance CO is obtained, and the amplifier is switched to its voltage clamp mode. Voltage reference may change it, causing large currents between pipette and bath, such as those that occur with the Lowe's-Watts method. Changing voltage reference will change the path membrane potential. Most PET amplifiers possess a 10-turn potentiometer labeled voltage hold or voltage pipette, which allows the holding potentials of the path to be altered. Pulses from one external source voltage command may be used to change voltage reference in a stepwise way. Generally, since noise applied to the head stage with the command signal appears in the current trace, the command voltage, and the noise applied with it is divided 10 or 50-fold in the head stage, requiring a command pulse 10 or 50-fold larger than the pipette potential but with better signal noise. For fast change commands, such as the leading edges or rectangular pulses giving rise to large currents due to charging, straight capacitance associated with pipette and the cell. This may saturate the amplifier and must be offset by adjustment of compensation circuits. Separate compensation is usually provided for fast primary straight and slow cell capacitance. 5. Particular attention needs to be paid to hearthing and screening. The signal hearth point of the amplifier should attach directly to the principal hearth point of the setup. The hearth or ground socket on the hand stage is connected with the cable to the signal hearth in the path clamp amplifier and is for connection of the path electrode. A metal surrounding the bath basable manipulators, dish holders, etc. And the microscope stage, nose piece, objectives and condenser should have low resistance, minor 0.5 ohms. Connections to the principal hearth point. This case of the hand stage amplifier may be connected to voltage reference to reduce charging transients during voltage steps. The case should therefore be isolated from hearth when it is mounted on the manipulator. Voltage reference may be available at the socket on the wheat stage with the intention that it might be used to minimize capacity current transistors by connections to screens near the pipette. Agard potential. 6. It is important to remember the convention for membrane current with outward flux of cations or inward flux of anions is positive. The output polarity of a path clamp may be more or menos resistor reference current pipette was determined by the internal circuitry after the head stage and therefore may be correct for Rayleigh cell recording and inverted for cell attached, as in the case in most commercial instruments, or may be correct for the cell attached and incorrect for Rayleigh cell recording, e.g. the biologic amplifier was this arrangement. 7. The following instruments are particularly useful for PET clamp work: a 4 or 8 pole low-pass filter, normally with a basal characteristic, an FM or digital VTR or the tape recorder, a computer interface and software for online voltage pulses and data analysis, and a wide bandwidth charge recorder such as a UV light pen, Mendeley or electrostatic type. 4. PET pipettes. Choice of glass. The very high resistance of the seal between cell membrane and the glass pipette means that some hydrophobic chemical interactions occurs between the two. The chemical composition of the glass may therefore influence the ability to form seals. Although the comprehensive review by R. Lewis 1992 of the properties of glasses of different composition indicates that the firm conclusions can be drawn concerning the ability to different types of glass to form seals. Other considerations that need to be taken into account in choosing electrode glass are as follows. 1. The ability to form pipette rolls types have appropriate size and taper factors that may influence the area of membrane isolate in a path or the series resistance in Rayleigh cell recording. 2. The degree to which background noise needs to be reduced. 3. Glass is doped with heavy metals as minor components to reduce the melting point. Heavy metal ions may leach into the pipette solution and modify channel properties. The composition and properties of different types of glass are discussed by Ray Lewis 1992. The following types of glass are commonly used. Soft, low melting point glass. This type of glass was initially used for PET clamp recording because it is easily pulled and shaped at relatively low temperatures, producing large aperture pipettes with blunt tips. It is not so commonly used to make recording pipettes, but can be useful for making large aperture tips or for cleaning tissue, slices, or drug application. Some soft glass contain lead or barium, and the hematocrit tubes are often made of this type of glass. Pyrex, borosilicate glass, corn type. Standard microelectrode glass is usually of this type, which is also most commonly used for PET clamps. For PET pipettes, pulling and polished require high temperatures, usually orange heat of a platinum white. Some argue then that the sealing properties are better than those for soft glass. Atrow, Hamill et al. 1981 stated that seals are less stable with glass of this type. Low resistance pipettes, tip diameter 1 a 3 micrometers, resistance 1 at 5 megaohms, are most easily pulled from this halide glass. Fake-walled pipettes generally seal better and they have lower noise levels because of the lower electrode capacitance. See below. The facility to backfill pipettes made from electrode glass that was a fused internal filament is particularly convenient. Glasses for low-noise single-channel recording. The current noise in high-resolution recording is influenced by the type of glass used because of differences in resistance and capacitance properties of the thin glass well at the tip. These properties are reviewed by Real Levels 1992. The most significant point noted are the large improvement in noise levels produced by Seaguard or other coating of the pipette shank with all types of glass, and 2. The considerable superior properties of quartz pipettes conferred by the low leakage conductance across the glass at the tip. Quartz softens at temperatures too high for conventional electrically heated filaments, and pipettes are pulled either with a gas oxygen flame or by a laser headed puller. Effects of glass on channel properties. 2 studies show that the type of glass used to make pipettes can affect chip properties of channel recordings. Code Armstrong 1988 showed that 2 types of low melting point glass soda or potash glasses produced additional fast inactivation of potassium channel currents when compared with channels properties determined with a borosilicate glass. This was subsequently shown to be due to most likely to baryon ion release from the soda glass. Found Tanaka 1988 compared the properties of CGMP activity channels in photoreceptor membrane recorded with pipettes made from one of 6 types of glass. They found differences in the current voltage relation that could be reserved when EDTA or EGTA, which bind heavy metals with high affinity, are included at millimoles concentration. Millimoles? I don't know. Concentration in the pipette solution with all but one of the glasses tested. These and the other reports indicate the necessity to avoid those types of glass that have been shown to affect channel properties and to test for contamination with chelators of heavy metals, and by comparing different glass types before used on channels of well-defined properties. Eu não sei se estou falando certo. A second potential source of contamination should be noted. This arises from the use of stainless steel needles for backfilling pipettes which are through told to be a source of polyvalent ions. It was also been reported that the hardness in some plastic syringes can block nicotinic receptors channels. Manufacture and fight pollution of pipettes. Pollution. Figure 4 illustrates the double pull producer used to make pipettes with a conventional wrapped puller. The solenoid is disconnected and the gravity alone provides the pull. Consistency in pipette formation can be increased if a digital voltmeter set to voltage RMS rodas por minuto por segundo meters segundo, não lembro, is used to monitor the voltage across the heating element. Fine polishing of pipettes is done with a rated PT ride mounted on the stage of a component microscope with stage movements or micro-manipulators used to bring pipette type and wire close together. High magnification 2200 at 400. Good quality optics makes this step easier to carry out. The tipped diameter of pipettes may be estimated before and after fine polishing by measuring the pressure needed to expel air bubbles from the tip into clean methanol. This pressure may be measured as the volume change applied to a 10 milliliters syringe connected to the pipette was a guide. Starting at 10 and using the scale, when the syringe a bubble number of 5 or less indicates pipettes of higher 10 megaohms resistance, suitable for cell attached recording, of 6 or more low resistance pipettes suitable for roll cell recording. This procedure is useful particularly when setting up a pipette puller. A meio produção de pipetas. Quoting pipettes to reduce capacitance. Pipettes used in single-channel recording are usually coated to thicken their walls and reduce capacitance to the bath solution. There are two reasons for wishing to minimize this stray capacitance. First, high-frequency noise levels are reduced, and secondly, as mentioned above, capacity currents associated with stepping that potential of the inside of the pipette are also reduced. The RMS current noise associated with stray input capacitance is given by. Here is the RMS noise for current and the voltage. F is the bandwidth, and C the total capacitance from input to earth. Current noise increases in proportion with voltage noise as the recording bandwidth is increased and also with the capacitance. The current needed to charge the stray capacitance on changing the pipette potential is given by current é igual a capacitância versus a corrente, voltagem por tempo, não, é a derivada da voltagem pelo tempo. And will be particularly large for a fast potential step, if at the leading or trailing edge of such a step. Derivation voltage per derivation time equal 100 millivolts for 20 microseconds. The current needed to charge a stray capacitance of 10 picofarads will be 50 nanoamperes, since a head stage with a 50 gigaohms feedback resistor will be saturated by a current that excesses 0.24 nanoamperes. See above. Saturation hold occur, and important information about channels that are rapidly activated by the voltage step would be lost. Generally, the fast capacitance compensation circuits of fast amplifiers have a range too small to compensate fully pipette capacities larger than 10 picofarads. Fat clamp techniques, uncoated article. Most of the stray pipette capacitance arises across the pipette wall between the pipette and the bath solution. It can be reduced by coating the pipette with a thick layer of Sealguard. 184. When an inert, hydrophobic, translucent elastomer resin rapidly cooled by heat. The coat both thickens the wall of the pipette and reduces the area of capacitance coupling by preventing the bath solution creeping up and heating the pipette. Coat should run from close to the rib flow tip, preferably closer than 2250 micrometers, and continue up the pipette well past the beginning of this taper. The procedure for coating pipettes and scoring the Sealguard are illustrated in Figure 5. As an alternative to Sealguard coating, pipettes can be dipped with back pressure before filling into a molten mix of paraffin in mineral oil or some other molten wax, or after filling immersed in a silicone coating such as sigmatode. Both these producers prevent fluid contact with the shank of the pipette and sticking in the wall at the tip. It is best to observe two additional measures to reduce stray capacitance. First, the depth of bath solution in contact with the pipette wall should be minimized. Secondly, the pipette holder should be kept free of excess fluid. Often, it is helpful to dry the holder with compressed air or nitrogen before inserting a new pipette. A discussion of methods for low noise recording is given by 1992. 5. Formation of a gigacell. As the pipette is advanced through the surface of the bath solution, positive pressure was applied to the inside of the pipette to keep the type free of contamination, either by mouth or from a manometer, a water-filled U-tube that permits fine pressure adjustment by changing the pressure head of water. The current is set to zero, either by altering voltage reference manually, with the voltage node control, or by using the search mode of the amplifier. The pipette resistance is then monitored by measuring the current in response to 0.1 to 0.5 millivolts step changes in voltage reference changes. Contact with the cell is indicated by a rise on pipette resistance. Gentle suction 5 and 20 centimeters of water is now applied to the pipette when a seal should be formed. Seal formation may occur immediately, or it may take some while to happen. It may be helped by polarization of the pipette to around -40 millivolts once a high resistance was developed. A fresh pipette should be used for each attempt to make a cell. The process of cell formation can be observed with good microscopic optics. Gigacells may form immediately on contact with the cell surface with very little negative pressure, particularly with high resistance pipettes. In these cases, the profile of the membrane is flat within the pipette tip. More often, an unshaped region of membrane is drawn into the pipette tip and the seal forms initially slowly and suddenly achieves a high value. Photographs are given of membrane pipette seals by Skalman, a near 1983, Milton 99, reports the formation of a blade of membrane lipid in the pipette tip based on microscopic observations of seal formation and proposed a role for the blade in forming gigacells. Gave a microscopic analysis of the pressure per area relations of membrane patches. Pressão por área. Membrane patches. Giant paths. Wilgeman, 1989, 90, 92, reports the use of various hydrophobic mixtures to facilitate the formation of the seals with large tipped pipettes. These include viscose, paraffin per oil, mixtures, and the alpha-tocopherol with minimal suction. These agents promote the formation of flat, stable seals desirable for access to the inner surface of inside-out paths. Liquid junction potentials. Here, differences in ionic composition exist between pipette and the bath solution. A correction must be applied for the junction potential across the boundary between the two solutions. This potential arises from differences in concentrations concentration and mobility of the ion species in the two solutions and maintains electron neutrality across the boundary between the two solutions. The magnitude depends on the relative mobility and the concentration gradient of ions diffusing in the two directions, and depending on the solutions used, may be 2 at 12 microvolts in physiological solutions. The error arises because the potential will be presented when pipette current is zeroed before sealing, but when the seal is made, the concentration gradient forms part of the driving potential for ion movement, leaving the applied offset potential still imposed in the pipette. With reference to the figure 3, the initial sequence of steps made during path recording are as follows. When zero current output of the amplifier is checked with the pipette out of the bath. This is usually 0 volts. 2. The pipette is put in the bath solutions and the offset current flows as a result of asymmetries in the AGCL half-cell potentials. The junction potentials across the pipette tip to bath and bath into the reference electrode salt bridge, and any voltage on the amplifier voltage reference. For present purposes, suppose that the AGCL cloreto AG não lembro. Potentials are equal and opposite, and the reference junction potential is 0, and so do not contribute. The current flowing into the pipette is driven by the difference between bath potential in the pipette potential and is set to 0 by adjusting voltage reference, which set the pipette potential with respect to the bath. In most bath amplifiers, this is done with a null potential control that changes voltage reference without registering to the voltage monitor. This value of voltage reference is taking a zero loading potential and is the zero current potential of the pipette with respect to bath potential. However, by convention, the polarity of the junction potential is bath minus pipette, opposite to the polarity of the voltage reference potential applied in the pipette. 3. A seal is formed and the liquid junction potential disappears, leaving the pipette potential displaced from the true zero by one amount equal to the initial pipette bath potential difference, opposite in polarity to the junction potential. In a cell attached or inside-out recording, the potential is on the outside of the membrane, and the true transpath potential is the loading potential minus the initial pipette bath potential, EA plus the conventional junction potential. For rolled cell recording on bringing to roll, a new junction potential appears between the pipette and the cytosol immediately on path rupture, and it disappears over the first minute or so as the cell is dialysed with pipette solution, leaving the initial pipette bath potential added to rolling potential. The conventional junction potential should be subtracted. The error due to the junction potential can be demonstrated and qualified fairly easily. However, it is necessary to have a reference junction that remains at zero when the composition of the bath is changed. This can be done with a 2 or 3 mega chlorated potassium solution in the reference salt bridge the stagely de cloreto. Não lembro. While your palette provides the junction between salt bridge and the bath is continuously renewed by slow outflow of chlorated potassium, for example from a blonde pipette some distance from the recording side. Also capture 1. Zero junctions potential is set the recording pipette by having the same solution in the bath would be in the pipette during an experiment. The potential is measured at zero current, whether in voltage clamp or current clamp, and is set to zero. The bath is changed to another solution, external solution, and the change in zero current potential measured. This is the excess potential that would be present in the pipette after CO formation and should be subtracted from the rolling potential in cell attached or added in roller cell to give the real membrane potential. Quantum potential. This problem is reviewed with particular reference to PAT clamp recording by Barry 1991 and by Neuer 92. The polarity was been given the conventional bath pipette opposite to the determined in the experiment above. The junction potential can be calculated from the Henderson equation given Barry 91. If the activities and the mobilities of the ions are known. As an example, in the simple but common case, here the bath contains 150 millimoles de chlorated sodium solution, while the pipette was an equal concentration chlorated potassium. The junction potential can be predicted from essa linda equação, eu não sei traduzir. Here, UNA, OK, and U chloreto are the mobilities of sodium, potassium, and chloreto, and EGP is the junction potential bath relative to pipette. Was in this case a calculated value of 4.3 millivolts, so the pipette will have an excess potential of minus 4.3 millivolts with respect to the bath. In roller cell recording, 0 millivolts input in the pipette will be minus 4.3 millivolts. In cell attachment recording, 0 will be. In cases where solutions differ more, particularly with chloreto ion replacement, the junction potential can be calculated with equations and the ion mobilities given by Barry, or taken from the measured values given by Neuer. Further problems arise when junction potentials occur at the reference bath solution junction. It is usual to have a salt bridge of chlorate of sodium bath solution between the reference chlorate electrode and the bath. This was the junction potential into the bath unless the external solution is changed, when a potential may arise and be added to the eroding potential. Producers for measuring liquid junction potentials and the discussion of more complex effects seen with external cell perfusion by dissimilar solutions are given by NIR 92. A second, but less common problem is that salts of low solutions reproduced, such as calcium or barium phosphates, fluoride or sulfate, may precipitate at the interface of pipette and body solutions. 6. Choice of preparation. The choice of a cell to use for single-channel work depends ideally on the experiment that is envisaged. In practice, the choice of a preparation can hinge on whether its cells readily make seals with glass and on the density of ionic channels in the membrane. Preparations that are used include cells from adult tissues, cell culture cells, channels and membranes of native lipid, and channels when incorporated into artificial bilayers as large vesicles, adult cells. These have to be cleaned of connective tissue and extracellular matrix using enzymes such as collagen and proteases. When a disassociation tissues, the presence of DNAs helps prevent clumping. However, individual protocols for enzymatic dispersal are empirically determined. In CNC tissue slices, the cell surface can be cleaned by irrigation from a cleaning pipette, and this procedure is increasingly applied to other tissues. The channel density is often very high in adult tissue. Sodium channels may have a density of 100 micrometers per meter or more, making it impossible to isolate a single or small number of channels. Culture cells. This provides the most widely used preparation for single-channel recording. Channel density is often lower than in adult cells, and the membrane may have less extracellular matrix. Commonly used primary cultures include myotubes and unexplained neural cultures grown from newborn rats or mice, from Xenopus larvae and from invertebrates. Various cell lines which provide convenient models for physiological processes are also widely used. Channels in active lipid membranes. Large liposomes or vesicles have been developed using freeze thawing of microsomes. Dehydration producers or chlorinated potassium and water loading of cells coupled with protease treatment. Whey corporation. Lipid membranes can be formed on the tips of pipettes and the channel reincorporate into these bilayers from microsomes. Such a method is particularly useful in the investigation of channels in specific membrane fractions. For example, these and related methods can be used to investigate channels in membranes of the transverse tubular systems of muscle fibers, or in intracellular membrane systems such as sarcoplasmic reticulum and endoplasmic reticulum. Não sei se lê assim, não. 7. Cell attachment recording. This mode of recording is used to study single-channel currents. The resolution of such unitary currents should be optimized by observing the precautions detailed above for reducing stray capacitance. Good mechanical stability and freedom from vibration are needed to keep cell attachment patches for long enough to record sufficient data. Activation of channels operated by binding of transmitters may be produced by having a suitable concentrations of transmitter or agonist in the path pipette. Opening of voltage activated channels may be achieved by stepping of potential inside the pipette. Often the pipette solutions will have the same ionic composition as the bath solution. Substitutions of ions may be made for studies of permeability properties of channels. The membrane potential of cell attachment pathways voltage path is determined by that of the cell interior voltage cell as well as by the pipette voltage reference. The membrane potential is therefore voltage do path é igual voltage da célula menos a voltage de referência. Generally, voltage cell is not known. Sometimes, for example, in large cells such as skeletal muscle fibers, it is possible to record this potential with an impaling microelectrode. Suitable analog means may be used to subtract in the from voltage reference, so that voltage path is the quantified monitored, breaking the membrane path at the end of the experiment with strong suction, so that the pipette is the contact with the cell interior, can also be used to obtain an indication of a voltage cell. Examples of currents through nicotine receptors activated by acetylcholine are shown in Figure 7, shows unitary potassium currents through the layered reactive channels of skeletal muscle activated by a despolarizing step. In these records, woodward membrane currents are shown as upward deflections, signs that they are, by convention, positive quantities. Most commercial path clamp amplifiers are arranged so that current flowing into the pipette or towards or across the membrane of cell attachment pathways produces a negative output. For clarity in description of their experiments, path clampers should be careful to use the correct convention for membrane currents and the membrane potentials. Aqui tem a imagem da corrente, retinho da plate, para 5 micromoles de acetilcolina, 50 micromoles e 500 micromoles de acetilcolina. Tá. Recording from expressed channels. Ion channels, modified by molecular biological producers and expressed in cell membranes, are used to study the relation between structure and function. They can be transfected in cell lines or expressed in channels oxytase by injection of mRNA into the cytosol or of DNA into the nucleus. Producers for recording from cell lines are the same as those described above. Recording from oocytes is technically more difficult because of the presence of accessory follicular cells and the vitelline membrane, which must be removed to gain access to the plasma lemma. Producers for treating oocytes for path recording are described by Maffassel et al. Aqui tem um canal, um PET clamp técnicas usando voltagem. Então isso aqui, se eu não me engano, é o potencial de ação. E aqui é o dobro dele para picoamperes. Single channel records of potassium channels currents in skeletal muscle fiber activated by a 55 milliseconds despolarization of the membrana potential from minus 100 millivolts to 0 millivolts. Cell attachment recording. Notary levels of current correspond to simultaneous opening of 0, 1, and 2 channels, produced by Stanford 0.80. Cell-free exit pathways. Inside the out paths are made from the cell-attached configuration as indicated in Figure 2. Pulling of a membrane path often results initially in the formation of a vesicle of membrane in the pipette tip. The outer face must be broken open, which may be done by briefly talking the membrane through the bath solution or interface by exposure to a low calcium solution or by momentarily making contact with a droplet of paraffin or a piece of colored sugar. Once the path is formed, channels activity are modulated by substances applied to the cytoplasmic membrane face may be studied. Such studies have included investigations of the effects of calcium, of catalytic subunit of protein kinase, and of ATP. Stones outside paths are formed after breaking into the cell with the producer. Calma aí. Indicator in Figure 2, such pathways have been used by a number of workers for the study of the pharmacology of channels activity by transmitters or hormones. And girders, these configurations of the cell-free mode often use the disadvantage of a higher level of background noise, probably because of a lower resistance of the cells achieved and because of the large area of the membrane in the path. Further, it has been reported that channel kinetics may differ when recording in outside out. Exist pathways from those found in cell-attached recording. Fast concentration changes to study neurotransmitter activity channels. It is important to be able to apply the neurotransmitter on a time scale similar to that encountered in the synapse within 1 millisecond. This can be achieved with outside-out pathways because of the very narrow inserted layer of solution adjacent to a path point when compared to the surrounding aerosol, where solution changes require tens of milliseconds. Methods for fast sub-millisecond concentration changes have been described by Mokonoshi Knight, 1989, and Louis Duggar, 91, utilizing electronic valves and with P's driving stepping of a strain of solution onto the pipette tip by Doodle Fraker. 9. Roll cell recording. Roll cell recording is achieved by rupturing the path of membrane isolation by the path pipette, which brings the cell interior into contact with the pipette interior. The processes of roll cell recording is as follows. After forming a gigacell, the fast capacitance transits associated mainly with pipette capacitance to the bath are compensated. Next, the potential of the pipette interior voltage pipette is adjusted to a level similar to the anticipated membrane potential of the cell. Rupture of the membrane path is achieved by applying strong suction or sometimes bring voltage transistors, and the process is conveniently monitored by the applying test pulses of 1 to 5 mV amplitude. Rupture is indicated by the sudden appearance of large capacitance transistors at the leading and trailing edges of the pulse. The sequence of change is shown in Figure 8. Series resistance errors in roll cell recording. The equivalent circuit used to represent the roll cell recording condition is illustrated in Figure 9. Current in the pipette defined for roll cell recording as positive flowing from pipette to cell flows first through the resistance series with the cell membrane to represent the pipette tip. If the series resistance is resistors and the pipette current is EP, a potential difference pipette cell of amplitude E results. This potential needs to be subtracted from the command potential to yield the cell potential. The series resistance compensation present in commercial path clamps allows a fraction of E vezes R to be added to the command to partly correct the error. Pat clamp técnicas, milivolts por corrente. Tô confuso. Cell attachment, roll cell. Figure 8. transistor's current due to stray pipette capacitance in a cell attachment recorded before and after. B. Cancelled with C first and the tau fast. C. Transistors due the cell capacitance in a Rowley cell recording with 5 mV rectangular input, 2 voltage reference, 2 kilo watts bending watts. Tô confundido. The cell capacitance. The pipette current was 2 components, once ionic voltage current per resistance current. Acho que é correto, não sei. And the other capacitance, C vezes derivada da voltagem pelo tempo. The time course of the change in the potential of the cell. Voltage cell from its initial value is a given by voltage menos voltagem infinita vezes 1 menos Euler elevado a menos t por tau. Changes on exponential curve of time constant. Tau é igual a capacitância vezes a resistência S, resistência C, dividido pela soma das resistências, não sei. Usually approximated really by tau C vezes resistor, because the resistência maior que a resistência. This time constant characterizes the response of the voltage clamped cell, not only to apply voltage steps, but also to currents originating in the cell membrane, with the therefore effectively low pass filtered with a bandwidth. The time course of the current following a studied change of voltage P, also shown in Figure 9, was a declining exponential time course. Initially, current flows mainly into the capacitance, since voltage 0 is stated at the beginning of the step in voltage P. The initial pipette current flowing into the cell discharges the capacitance and is given by E is equal to 0 voltage per resistance. The pipette current declines exponentially with tau equal capacitance resistance to the steady level. The size and the time constant of the error voltage due to series resistance is minimized simply by keeping resistance as small as possible by using low resistance pipettes. If the last conditional is kept, it may be expected to hold in most conditions. And for small currents, when using Rowley cell recording, it is important to know the errors that arise from series resistance and cell capacitance. These quantities may be estimated from the current transistors shown in Figure 8 and 9, provided RS menor que RC. The area of the transistor, which gives the charge on C, is equal to C vezes voltage P, while the time constant of the decline is given by tau, e essa conta de novo. The area may be estimated by digitalizing the current recording and in integration the time constant by curve fitting. Estimated of resistors igual a voltagem dividido pela corrente. Acho que é isso. Não lembro. From the initial amplitude of the transient are subject to error because the rise of voltage usually was a time course of 10 to 20 microseconds, and because of low pass filtering typical values of the series resistances are 3 a 20 megaohms if low resistance. 1 a 5 megaohms pipette are used. The resistance may be as high as 50 megaohms. However, and is liable to fluctuation during recording. For a series resistance of 10 megaohms and a cell capacitance of 12 picofarads, corresponding to a spherical cell of 20 micrometers diameter of membrane capacitance, 1 microfarad por centímetro quadrado, tal igual a 120 microseconds for settling of the clamp and the FC 1.3 kHz. Kilohertz. The currents associated with charging the cell capacitance should be compensated using the slow capacitance compensation of the path clamp amplifier. The system injects current into the pipette to cancel the capacitive currents, avoiding saturations of the head stage during large voltage pulses. In most path clamp amplifiers, this low capacitance compensation is separately switched and was controls for the size of the capacitance and the time constant, or series resistances of the decline of capacitance currents. It is important to note the capacity compensation subtracts capacitive current from the amplifier output. It does not compensate for the slow change in cell membrane potential due to series resistance. Most commercial amplifiers have a separate series resistance compensation which allows a fraction of the pipette current times series resistance to be added to common voltage using conventional voltage clamp. See capture on voltage clamp techniques. This works best if resistors is small and should be used with caution because of frequently fluctuations of resistance during recording. To the extent that the best producer is the monitor and adjusted the compensation digitally via an interface immediately before each voltage command. A second way of detailing with series resistance in roll cell recording is to use a switched discontinuous single electrode voltage clamp in which the membrane potential is monitored at zero current flow. So elimination the error voltage due to E currently. See capture 2. Switched clamps have inherently greater noise than as 100 found than path clamps and can only be used with large membrane currents. Diffusional extensions between pipette solutions and cytosol. In conventional roll cell recording, the contents of the interior of the cell come into the functional equilibrium with the solution in the path pipette. It is achieved more rapidly for ions than for large intracellular molecules, which do however get washed out of the interior of the cell in time. The time course of exchange depends on the size of the pipette tip and the cell volume, as well as on the molecular size and the degree of buffering by cytoplasmic constituents. The advantages are control of the intracellular ionic composition and the perfusion into the cell of agents such as dyes that indicate ions concentrations, secondary messages, and caged secondary messages, antibodies to intracellular proteins, and small proteins generally. The disadvantage is the loss of important cellular components, including small proteins, into the pipette. Pipette. Figure 9. Equivalent circuit of a roller cell recording. Current in the flows in the cell resistance and in the capacitance. Pipette current E igual E mais E flows in the series resistance between pipette and the cell that produces a voltage error. Voltage menos voltage igual times course of changes of voltage and the current following a step of esse circuitinho que eu tenho que revisar eletromag. The time course of equilibrium of ions de sódio during roller cells recording was reported by Fenwick, Marff and Neuer, 1982, to have a time constant of about 5 seconds in chromatin cells judged by changes in the NER current. Junction potentials due to small ions will exist between pipette solutions and the cytoplasm. The sources of error will not be a constant, but will change towards zero as the equilibrium between pipette and the cellular contents proceeds. 1983. Estimate a maximum error of 12 millivolts from the source. A displacement of the potential dependence of ionic currents that occurs during roller cell recording may be related to this changing junction potential. The time course of equilibration of larger molecules is much slower, particularly if they bind to cellular components or the metabolism. For molecules such as fluorescent, these of may number 500 1000, the equilibration judged by the fluorescence increase takes several minutes, and it depends very much on how good the access is through the pipette tip. Observation suggests that as well as a low access resistance, it is important to minimize the amount of material taken into the pipette tip during CO information. An analysis of the time course of equilibration of the strong target ds as a function of size and the access resistance was been made by Puig. They present evidence that components of up to about 20 kilodaltons may be lost from the cell. There are well-documented instances of changes in the properties of ionic currents, and also cell responses involving secondary messengers that occur during roller cell recording and which can be attributed to loss of cytosolic components into the pipette. Best known is the rundown of slowly inactivation calcium conduction that occurs during intracellular perfusion. Evidence suggests that This is lowered by inclusion of ATP and magnesium, acho que é magnésio, in the pipette, and may be improved by inclusion of protease inhibitors such as leopeptin or phosphatase inhibitors. Loss of the calcium mobilizing hormonal response of exocrine cells during conventional Rowley cell recording was noted by Ron Martin, 1988, who introduced the method of path permeabilization to prevent the rundown of the responses. Instead of rupture by pressure of the membrane wonder, the pipette they achieved electrical access to control the membrane potential by including the ionophore nistidina, ionofosfato de sódio nistidina, não sei agora, in the pipette solution, preventing loss of high molecular weight components. The method was then used with other ionophores, such as amphotericin, não sei como se lê isso, and the bacterial toxin, alpha toxin from Staph aureus Kotler et al. 1992, that makes pores large enough to admit these and Kaged second messengers menor do que 1 kilodalton. Permeabilization is generally more difficult to implement than path rupture because the ionophores prevent CO formation and they are unstable in solution. Use was also been made of the exchange of cell and pipette constituents during Rowley cell recording to change the concentrations of internal ions and of other substances in systematic way. A perfusion system that takes account of the technical problems encountered was been described by Soejima e Norma 1974. Measurement of changes in membrane capacitance. The facility of a Rowley cell recording to make precise measurements of membrane capacitance was been developed as a method for measuring changes in membrane area that occur during exocytosis. The procedure is to analyze the admittances of the Rowley cell equivalent circuit into components due to capacitance, series resistance, and membrane conductance by use of a please-looking amplifier. The resolution is sufficient to see unitary changes associated with the incorporations of single, albeit giant, vesicles into the cell membrane, and it was given considerable information about the processes of vesicular membrane fusion. Revealed by Almers, by technical descriptions of the methods are contained into the initial reports. 10. Identifications of ionic channels. The nature of ionic channels may be identified by when the mode of activation 2. The permeate ions under physiological conditions. 3. The unitary conductance, and 4. Selective broke by drugs, ions, or toxins. 1. Ionic channels may be opened by the following. neurotransmitters and chemical analogues acting on external receptors coupled directly to the channel opening mechanisms. The open probability of these channels depends on transmitter concentrations, and they are usually involved in fast synaptic transmission. Examples are nicotinic acetylcholine channels and glutamate activity channels. B. Membrana potential, for example, sodium, potassium, and calcium channels opened by despolarization during and the action potential. Action potential. Calcium channels by opening. C. Intracellular ion concentration or other cellular constituents channels closed by internal ATP. The opening probability of some channels is modified by intracellular secondary messages released by hormone action. An example is the calcium channel or cardiac muscle after phosphorylation by CAMP-dependent protein kinase. Most of these kinds of channels are also opened by one of the above means. 2. Once a channel is opened, then ions that permeably can be determined by measurement changes of the reservoir potential and the unitary conductance when the concentrations of ions in the external or internal medium is changed. 3. The unitary conductance under specific conditions may vary considerably among different channels with the same ion selectivity. For example, there are at least 3 types of calcium activated potassium channels distinguishable on this basis. 4. Some channels are blocked selectively by low concentrations of drugs or toxins. For example, block of NA channels. Calcium, sodium channel of external tetrodotoxina of delayed rectifier potassium channels by TA derivations or of nicotinic acetylcholine channel activation at the neuromuscular junctions by alpha-bungarotoxin. Blocked by other agents may be less selectivity. For example, block of NA or acetylcholine channels by local anesthetics or calcium channels by quinine. Bom, é isso, acabou-se. Tchau, tchau. Obrigado por tudo.